On page 86, we're going to start section 6.2, looking at logarithms. When I first started teaching this kind of material, and I was trying to find the best way to sum up what logarithms are in a simple sentence, the best way would probably be that logarithms are exponents. So logarithms and exponentials are related deeply. So we'll talk about this in just a minute, but there are a few little housekeeping things that you should probably know. The first thing is that logs are an inverse function for an exponential function. So only one-to-one functions have inverses. We talked about one-to-one functions in the last section. But only one-to-one functions have inverses. So if you have a function, but it's not a one-to-one function, then it does not have an inverse. A log is a method to move a variable out of the exponent spot. So sometimes you'll have an equation, and the x is up in the exponential spot, and you need a way to move it out. So what we do is we have logarithms. It's a way to invent, it was a way that was invented to rewrite an exponential and move that exponent spot around a little bit and give you some movement for if you want to try to solve for a variable in the exponent spot. Logs can be used to rewrite equations that have a variable in the exponent spot. Here we have a exponential equation wrote 2 raised to the power of x equals y. I can rewrite this as a log, and it's actually not as complicated as it looks. You first start by writing the word log. The base that you have in your original exponential becomes the base here. So we call this log base 2. And then what I'm going to do is I'm actually going to take the variable that's up in the exponential spot and what's on the other side of the equal symbol, and I'm going to have them trade spots. So this becomes log base 2 of y equals x. Again, log base 2 of y, and then we have that equal to x. Notice that x was in the exponential spot, and after I rewrite something as a log, it now becomes something that is not in the exponent spot. So if you were asked to rewrite some of these in log form, I'm going to do the first one with you. I'm going to write the word log. The base becomes a small subscript number right next to log. So far this is log base 5. And then I have to interchange the x and the y. So the y becomes big and it's on the left-hand side, and the x becomes big and it's on the right-hand side. These are equivalent statements, just written 2 different ways. One is in exponential form and one is in log form. Go ahead and pause the video, do B and C. You're just rewriting these in log form, and then you're going to come back to the video and compare your answers with mine to see if you're doing it properly. B is going to be log base 8 of y equals x. C is going to be log base 6 of y equals x. And these are pretty similar to the last 2 examples, so hopefully you didn't have too much issue rewriting those, because not all of them are that pretty. When we try to find the inverse function for an exponential, and we're trying to solve for the input variable, usually this will lead us to a basic problem, and that is the fact that you have a variable up in the exponential spot and you want to get it out. So let's look at our first little example here, f of x equals log base b of x. Again, you're going to read this as log base b of x. If there is no number in the b spot, you can assume that that number is 10. So that is a thing, and that's going to come into play here very shortly, and I'm going to have you recall this. And just so that you are aware, if you have a function that is an exponential and you want to find the inverse of it, it would look like log base 2 of x for this very first example. If you started off as your with your original function being log base 2 of x, then its inverse is 2 raised to the power of x. We'll come back to this in a little bit, but important for you now to just start to become familiar with the setup. Okay, so what we're going to do for the next example, what I'm going to do actually, because I want to keep this simple, is I'm actually going to set all of these equal to x so that we are able to use the same format for switching these from log form to exponential form as we were learning on the page before. They want us to evaluate these logs by rewriting them in exponential form. Well, we've been writing exponentials in log form, but we haven't been converting logs to exponentials. It's not much different. The base that you have here becomes the base of my exponential, and then these two parts will switch spots. So this will be 5 raised to the power of x is 25. We do what we call solving this by inspection. Usually that means that you are able to use your knowledge of powers to be able to solve for x. What power of 5 is 25? 5 squared is 25, so x must be 2. Looking at b, if I rewrite this as an exponential, the 2 becomes big. My x and my 16 switch spots. What power of 2 gives me 16? Well, I have 2 times 2 is 4, times 2 is 8, times 2 is 16. So that would mean the 4th power. 2 multiplied by itself 4 times is 16. Looking at C, I don't have anything written here in the base spot. And at the bottom of the page that we just looked at previously, I told you if there is no number here, you can assume that number is 10. And so if I was going to rewrite this as an exponential, this 10 becomes big and the x and the 1000 switch spots. A little bit of a tip when it comes to powers of 10. If you can count how many zeros are in the result, that is the same number that's going to go in your exponent spot. So if I have 1000, that's 3 zeros. That means that 1000 is equal to 10 raised to the power of 3. So x is going to be 3 for C. Take a moment, you're going to do A and B, and then I want you to come back and compare your answers to mine. So take a moment right now, pause the video. For A, I have 10 raised to the power of x equals 10,000. So x must be 4. There are 4 zeros there. For B, 7 raised to the power of x equals 49. So x must be 2 because 7 squared is 49. Properties of logs. So just like any other math tool, there are certain things that will make your life a little bit easier if you're aware of them. So the first property is if the log of 1 for any base logarithm, it will always be equal to 0. So if you have any kind of base, so I'm going to say log base 5 of 1, or I'm going to say log base 12 of 1, or log base 8 of 1, remember that if you're going to have these equal to something and you're trying to figure out what that something is, you can change these to exponential form. So this base 8 becomes the big base, and the x and the 1 switch spots. Notice that anything raised to what certain power will always have a result of 1. That power must be 0. 8 raised to the power of 0 is 1. 5 raised to the power of 0 is 1. 12 raised to the power of 0 is 1. All of these are going to have an x value of 0. What is the clue there? If you have a 1 in the spot right after your log base, then you know the whole result of this will be 0. Number 2, the log of its base is always equal to 1. So notice that on this example here that my log base b of b, the thing there is that it says b of b. If I have log base 3 of 3, it's going to be equal to 1. Why is that? If I change this to exponential form, 3 raised to the power of 1 is 3. If I take something like this and I change it to log or to exponential form, 7 raised to the power of x is 7. X must be 1. If your base and its number or whatever you have, even if it's a letter, if this is log base c of c, you will always know that the result must be 1 if these two things are the same variable or number. Number 3, the log of its base to a power is just the power. So this is a little bit different from the one before. If I have log base 4 of 4 squared, and I want to write this as an exponential, the 4 becomes big, the x comes over here, my 4 squared goes on the other side. The only way for these to be equal is for their exponentials or their exponents to be equal, so this must be 2. Notice that if these two are going to match and you have an exponent here, then the result of the whole thing must be that exponent. So if I have log base 7 of 7 cubed, the answer to this is going to be whatever's up here in this exponent spot. If I have log base 9 of 9 to the 5th power, the result of this is going to be 5. As long as these two things are matching, the result is going to be the exponent. Okay, so we're going to evaluate the following logarithms using the property of logs. So I just have to erase the title I have up here because I think that that is an error. Again, I want you to remember that this is log base 10 of 10 to the 5th. If I wanted to evaluate this, remember that if you have matching base and number next to it, the result must be the exponent. If I have an example like B, remember that if you have 1 in the spot next to the base, then your x must be equal to 0. That was the very first one that we did. For C, your base and the number next to it is matching, so the result for this must be 1. Those are all examples from the 3 properties from the page before. At any time, if you don't remember those properties, it's okay, because if you just change these to exponential form, you will figure out what they are equal to. Go ahead and do A and B, and then I will go over these with you in just a moment. Okay, so for A, I have matching base with the base of the power, so this must be the power. And then for B, if you have 1 in that spot, then the result must be 0, because 4 raised to the power of 0 is 1. Sometimes you're going to have situations with logs where your numbers are not going to be perfect squares or perfect cubes or perfect 10th powers. You're going to have something that the result of it is going to be a decimal. And unfortunately, we wouldn't be able to have an accurate decimal figured out with a human hand. You would have to put this in a calculator to figure out what it is. So I'm going to go ahead and Desmos, and I'm going to put this one and this one. And I want you to do it also, and I will paste the result in underneath here. So just give me one moment. Okay, so for the first one, log of 500, when I went ahead and put that in Desmos, it gave me this long decimal. No big surprise. We have this other one that says ln. You will find this in the same area of Desmos that you would find log, which is tools that are down in the right hand corner. There's 4 different tabs. The last tab, I believe, says miscellaneous. You can find the log function in there and the natural log function, which, by the way, that's what ln stands for, natural log. We'll talk a little bit more about natural logs in a few pages. I just want you to get used to the fact that even though the letters are backwards, this stands for natural log. A lot of times my brain processes this when I read it. I read log natural because that's how people read left to right. But that's not how it is actually supposed to be in the math world. So that's a thing. Okay, so looking at natural logs a little bit more. They work the same way as regular logs, except instead of using log, we use ln. And instead of base 10, we do what we call base e. So remember before when I was telling you that if there's nothing written in the base spot here, you can assume it's 10. If I have the natural log of 10 and there's nothing written in the base spot, the base for natural logs is a number we call e. If you go to Desmos and you put e in, you'll notice that it's actually equal to a number. So e just represents a number. Just like pi represents a number, which is the number 3.14, and then there's an approximation that goes on and on and on forever. E is the same way. It's just a number, but e goes hand in hand with natural logs, and we will have time to look at that a little bit further. If we're talking about real-world problems, we usually use natural logs in the instances where we are using exponential functions to predict numbers that are being compounded continuously. Continuously, that's the key word right there. But again, we're going to go over that several times, so you'll see that a little bit more in the future. Okay, let's talk about the change of base formula. The reason that this kind of was started was because when we first started evaluating logs using a calculator, and you had something like the log base 6 of 25, and somebody wanted you to evaluate this and find out what it's worth, we don't really have a beautiful power of 6 that gives us 25. So we know this exponent is going to be some kind of decimal. And our calculators were limited. We couldn't put a subscript number in there. We needed a different way to write this. So they created what we call the change of base formula. The change of base formula basically says, if you have a log with a base of a number, you can rewrite this as a log of the big number over the log of the base. And this is very easy to put in the calculator and evaluate something like this, which may or may not be easy to put in the calculator. So it's really not as complicated as it looks like it should be, but if you were going to change these and use the change of base formula, A would look like log of 114 over the log of 5, and I would put that in my calculator that way, and I would get, okay, so here's the example. I'm actually going to cover up the other one that I had here. I want you to notice that if I had put this in the calculator the original way, my result would be this 2.94276555299. If I also put this in the change of base way, you get the exact same answer. So it's really important to know both ways, just because sometimes it will come in handy if you get stuck. I want you to take a moment and go into Desmos and practice putting all three of these in the calculator and giving me the decimal that they are equal to. Then you can come back and check your answers with me. Okay, so we have the very first answer to B right here. The answer to the A that's below here is right here. And then the next B is here. Notice that this last one I put in change of base form. The other two I put in Desmos just the way that they were on the notes. Okay, so this whole section has been revolving around being able to write exponentials in log form, or to take something from log form and make it an exponential. I think that this is a very good graphic for you to be able to match up where things are moving by color. So the only thing I would do different about this is when I rewrite logs, I tend to keep the power on the left-hand side. So what I usually do is I make that B big, and then I switch the M and the N, and I don't put the power on the other side. It's just a thing that it's something I preference. Yeah, I don't think I said that right. The base of the log is the same as the base of the related exponential functions. Basically what I just said. And then you can see another example right here. And a reminder that anytime you have an exponential or any one-to-one function and its inverse, the domain of the original is the range of the inverse. And the range of the original is the domain of the inverse. It's just an interesting little tidbit. Okay, so what they've given us here are some exponential equations that actually are worked out. You're not solving for anything. It's actually just a statement, but they want you to rewrite it in log form. For instance, A, I'm going to write the word log My 7 becomes that small subscript base, and these two pieces get switched. And now it's log form. Go ahead and do B. Come back and see if you got the same answer that I did. For B, I'm going to write log. 4.5 becomes the subscript, and then 91.125 and 3 change spots. Now that is in log form. You should be able to do this going in the opposite direction. These are not exactly equations that need to be solved per se, but you can rewrite these in exponential form by making the subscript base big and then interchanging the 5 and the 243. And this is a true statement. If you put this in the calculator, 3 raised to the power of 5 is 243. D, you take that 2.5 and make it big. Switch these two spots. Now you have rewritten that statement in exponential form. I want you to notice again, we have a function that is an exponential, and if it is graphed, which it is here in blue, we are familiar with exponential graphs because we went over them in section 5. I want you to see that if you were to find its inverse, the inverse of an exponential always has to be a log. If you were to graph it, it still does that thing where it reflects over the line y equals x. So this acts as the mirror, and the blue is mirrored by the red on the other side. So what happens when they ask you to find the inverse of a function? I'm going to go through all of the steps that we were going through before, even though these are exponential and log functions. Just remember, if you ever get stuck, rewrite it as the other thing. So if you're in an exponential function and you get stuck, rewrite it as a log. And if you're in a log function and you get stuck, rewrite it as an exponential. Usually what you need to happen will happen somehow or another if you remember that simple rule. A, I'm going to rewrite it. F of x is going to become y raised to the power of 3 raised to the power of x. I'm switching the x and the y, and I now need to be able to get y out from the spot. So I'm going to write this in log form. Log base 3. Y and x are going to change spots. And now I've gotten y alone. And so I can rewrite this with function notation. The inverse of f of x is log base 3 of x. If I look at b, I'm going to do y equals log of x. I'm going to interchange the x and the y. I want to be able to free this y. The only way I can do that is to convert this to exponential form. Remember, if there's no number here, we can say it's 10. So 10 becomes big, and the x and the y change spots. 10 to the power of x equals y. So my g of t inverse is 10 raised to the power of t. For C, I am going to rewrite this without function notation, switch my x and y. I want to get y alone. I actually can divide both sides by 5. That gives me 4 raised to the power of y equals x over 5. Now I need to be able to get y out of the spot, so this is the point where I change it to a log. Log base 4 of x over 5 equals y. So I can rewrite this in function notation, but I want to make sure it's proper. So I'm going to have to say h of x, the h inverse of x equals log base 4 of x over 5. D is interesting because you see that letter E. And I told you wherever you see E, you have to use natural logs. So here I am, y equals e to the power of x equals e to the power of y. I'm going to have to change this to log form. So I'm going to start with natural log. This e becomes the small thing here, and then x equals y. So my inverse is natural log of x. Remember that e is already going to be assumed to be the base if there's nothing written here. So if you do write the e there, that's fine. But if you don't, then it is assumed that there's an e there. Okay, this is the last page for this video. We're going to solve each log by rewriting in exponential form. Do you notice we just keep doing this over and over and over again? Writing things from exponential to log form or log to exponential form. If I rewrite this in log form, this is a 10 right here. So I'm going to say 10 raised to the power of 2 equals x. Well, that must mean that x is 100. If I change this to exponential form, the 4 gets big, the 5 and the x change. Spots. 4 to the power of 5 is x. And I could put this in my calculator either by putting it in as 4 caret 5, or I can rewrite it several times on its own and put in the final answer, which is 1024. Here's another one. Solve each log equation by rewriting it in exponential form. If I rewrite this, this would give me e raised to the power of 4 equals x, because remember there's an e in this spot. This is just a number, so I'm just going to go to Desmos and put e raised to the power of 4 and see what that number is. It's going to give me some kind of decimal. In this case, it's 54.598. Looking at b, I'm going to change this to exponential form. 2 raised to the power of 6 equals 5x. If I want to get x alone, I'm going to divide both sides by 5. So what I'm putting in my calculator is 2 to the power of 6 over 5, which is 2 times 2, which is 4 times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. It's 64 over 5. I'm going to leave it that way. If WebAssign wants you to put it in as a decimal, you just put it in the calculator and find the decimal form. That's the end of this video. You're probably going to have to watch it more than once. It's a lot. If you have any questions, post them in Schoology or attend the next Zoom session. Good luck.